So in this particular lecture, we will just do a recap of the fundamentals of fluid dynamics, which will be handy. So we have already taught, we have gone through the mathematics. This is just an overview. So what is a fluid? Anything that deforms continuously under the application of shear stress, and fluids includes both liquids and gases. Okay, so the deformation and the equilibrium part, the fluids including liquids and gases possess the ability to deform continuously under the application of an external force. So unlike solids, the deformation is reversible to a certain extent. The fluids lack therefore an elastic limit, so to say. In solids, however, the equilibrium implies the absence of deformation. In fluids, equilibrium refers to the state where deformation remains constant. All right. So then there is a concept of stress and strain. So shear stress represents the force that is applied tangentially to the surface by the fluid, okay, and divided by the area. And the shear strain is the angular deformation that actually happens. Okay, so the relationship between shear stress and shear strain represents its resistance to the deformation. Then viscosity, also the definition of viscosity, it is a property that gives measure of how much resistance the fluid offers to the flow. It is also defined as a resistance offered by one layer of fluid to the subsequent adjacent layers. Okay. So with temperature, viscosity increases for gases, but however it decreases for liquids. So if the fluid is called Newtonian, then we have the constitutive relationship, which basically links the shear stress with the velocity gradient. This is the cross velocity gradient, and mu is the coefficient of viscosity. Okay, this adheres to a linear relationship between shear stress and shear strain. Okay, so the viscosity remains constant under different shear strain rates, making them relatively straightforward to analyze. So this is the velocity gradient, for example. This is the u velocity varying in the y direction. The examples of Newtonian fluids includes water. These are all things that we did. Then if you talk about non-Newtonian fluid, it is the fluid which exhibit complex behaviors, like shear thinning is, for example, shear thickening is another example. This behavior arises due to the response of the fluids to shear forces. It's not as simple as what we saw over there. Polymers can be one example of a complex fluid. Okay, so each of these things has a microscopic origin. So when you look at fluid dynamics in the macroscopic world, you have pressure, volume, temperature, etc., etc. All of these occurs in the microscopic world, where the positions, velocity, and the mass of each atoms or molecules actually jitter, and that leads to the manifestation, or the interaction at the microscopic level leads to collective interactions, leads to higher level organization, giving rise to this kind of properties that we see in the macro scale world. So each of them has got an underlying microscopic theory. So on a microscopic scale, for example, the fluid exhibits perpetual disordered motion. This is like their kinetic energy. They can also rotate. They can have rho vibrational energies as well. So the temperature serves as a gauge of the mean kinetic energy of the fluid within the material for translational motion. Okay, as for example, this has more thermal energy, this has less thermal energy. So if the temperature rises, the average kinetic energy also goes up. So the pressure is basically generated by the gas from the multitude of molecular collisions that occurs at the boundary and at the enclosure. In motion, the molecules collide with the container walls, producing a force that is directed perpendicular to the wall. So overall pressure exerted by a fluid is a cumulative effect of all these molecular interactions that you see. So similarly, velocity on a macroscopic scale, the fluid velocity is you can define it using a velocity field. It's typically the Eulerian representation, and there is vectors at each point in space, which actually varies with time. So the collective motion, however, emerges out of molecular collisions. The velocity field reflects the overall movement of these fluid particles. So different regions can have different velocities. So there can be spatial gradients of velocities, and there can be temporal and spatial variations of velocities in all four dimensions. Then comes the concept of cohesive forces, particularly important because later on when we do PDPA, LDV and other things, when we use droplets, for example, so you need to know a little bit about cohesive forces and surface formation. So basically when you actually have, for example, this is a container containing some liquid. Now the molecules which are at the center actually have forces which are very occurring in the same way in all directions, so they are in balanced condition. But however, the molecules which are at the surface, they have unbalanced component of the forces. So this leads to surface tension. It is a consequence of these cohesive forces, okay, which this actually brings about phenomena like generation of droplets and capillary action, okay. So these forces empower the surface molecules of a liquid to adhere to one another, giving rise to the formation of this well-defined boundary or an interface that you see over here. Then, of course, the concept of no-slip boundary conditions extensively used when you actually do wall-bounded flows and stuff like that. So the velocity at a stationary wall, the relative velocity between the fluid and the wall is 0. So therefore, the wall has the same tangential velocity as the fluid. So they are actually do not have relative velocity between them. All right. So this is the most important part that you should keep in mind. This is, for example, flow over a flat plate, which is a canonical fluid dynamics problem. All right. Then, of course, the concept of Lagrangian and Eulerian kind of description. So, for example, in the Lagrangian, what you do, this we already covered in details. The main focus is that you track individual particles, fluid particles as they traverse. But we said earlier that this is a near impossibility to do. Okay, but this is the path of the trajectory, for example, of a fluid particle that describes the motion. Eulerian is, however, that you monitor certain spatial points and monitor the evolution of the fluid characteristics at those points. So instead of following individual particles, the emphasis is placed on observing fixed spatial locations for the fluid properties. So that is a Eulerian for you. So if you, Eulerian is therefore a field representation, and it is extensively used in fluid mechanics, as we already know by this time. So this is, for example, a field equation for velocity. So the mathematical field is a mathematical function, if we have to define what a field is, that assigns a value to each point in the space. In fluid dynamics, various fluid properties such as velocity, temperature, pressure, density are represented as fields. Okay, so it is very useful to visualize the flow field using this field technique. For example, this shows a vorticity, velocity, and streamlines all in one. So it allows you to create visual representations like contour plots, streamlines, which enables us to get insights into complex flow patterns. And PIV, as we will see, is exactly a field representation. All right. So this is, for example, some visualization. Okay, for example, this is behind the, behind an aerofoil, okay, tilted aerofoil, and how the flow separation actually happens. And this is like a vortex, and this is another, shedding behind a body. So in all these cases, you see that there are visual cues that plays a very strong role in how the fluid behaves. Now there are, as we already talked about earlier, there are different ways to represent the flow field. We can have streamlines, which focus on instantaneous flow characteristics. We can have streak lines that track the history of particles passing through a fixed point. So you are acting like a customs officer. And the path line traces the actual paths followed by the individual particles. So all of these are very useful ways of representation. So these are, for example, path lines. The path lines are actual trajectories followed by individual fluid particles as they move. So this is a long exposure photograph of a campfire which shows the path lines. So path lines are valuable tools because it enables you to get insight into the prolonged behavior and the movement. They also can tell you that how cohesive the path lines are. So understandings that how the transport might have happened, especially in complex flows, this is a very useful tool. So you can see that how this is actually very useful in detecting this. Then, of course, the path line has got a mathematical formula. The path lines are basically specified by dr by dt, which is u. This is like a Lagrangian description. That's how the position vector is changing with time, and that is the path line. So, and of course, you have an initial position, which is r naught, and then how it evolves over time. So, this is like how this vector actually changes. The position vector changes with time. So, path lines depict the history of the particle's motion over a period of time. And then, of course, there is the streamline, which you already know. The streamlines are such that it is how it is constructed. So, everywhere in the streamline, the flow velocity is tangential at that particular point. So, these are imaginary lines that you can see. The fluid flow field is always tangent to the instantaneous velocity vector at every point. So, in other words, it gives a representation of a fluid parcel that would move if it was placed at this particular point. So, they are crucial for the understanding of local behavior of the fluid flow. This enables us, scientists and engineers, that how the fluid will behave around objects, aerodynamics and other things. Okay, so this is also useful for representation of, when you want to represent PIV. So this would be one of the key features of that. Okay. So streamlines have this mathematical representation, which is x, y, z is the coordinates. So dx by du, dy by dv is equal to dz by w. So here x and u, x is a corresponding coordinate system, u is the corresponding velocities. So this is the instantaneous picture that is actually represented. To solve this equation, you need to choose a parameter. And then later integrate this parametric equation. So streak lines are paths traced by a fluid particle passing through a specific point. So if you are monitoring at a particular point and you are seeing all the particles, the paths that are traced out by it, so it provides information about the temporal evolution of the fluid field and is very useful for unsteady flows. So for example, this is a laminar flow. These are the flows with eddies. This is a highly turbulent flow. They have injected some dye in water. And this also you can see at a specified location. We are able to see that how the smoke injection, for example, happens. So each of them has got their own advantage. So if you look at the flow visualization situation, you will see path lines, streak lines, and streamlines. Streamlines are obviously those dotted lines, and the red and the blue are the path lines and streak lines respectively. So you can see the red particle moves. The red particle moves in a fluid following the flow exactly. The trace is actually a path line. The end point of the trail, which is trail of the blue path, which is initially released from the starting point, adheres to the moving particle. So however, in contrast to the unchanging path line, the ink released afterwards interacts with an alternate flow field. Okay, so the dashed lines represent the velocity contours and illustrating the entire field's movement at any given point. So these lines are streamlines, and the velocity at any point is tangential to the streamlines. So this is just a demonstration of how the path line and the streamlines and the streak lines actually vary from one another. Okay, now we have already covered the concept of material derivative. So if we consider an Eulerian quantity Q, which is fixed at a fixed position in time, then for a fluid element which is at a time t at that location, and the value of that quantity is qrt, so the Eulerian velocity at that point is vrt. The position of the fluid element is this. So therefore the rate of change of q of the fluid element, which is an Eulerian quantity, is denoted by capital dq by dt, which is given by this. Okay, so if you use a Taylor series expansion to the first order, so you get something like that. Okay, so the Taylor series expansion with respect to a scalar gives you something like that. This we already covered. So if you substitute everything, you will get this. So the material derivative is, or the Lagrangian rate of change, or the substantial derivative, or the total derivative. It is basically the unsteady term plus there is a convective term associated with it, or advective term. So the time derivative follows this kind of a formulation. So this is the local rate of change due to time variations of q at a particular point, at a fixed point. Then this is the convective rate of change because of the fluid element being transported to a different position along the gradient of q. So instead of scalar q, it can be also vectors like position, velocity, momentum. It can be anything. So this is what the material derivative was all about. So, there are other approaches using multivariate calculus. We can also show the total derivative, okay? And these are different ways of, showing that how the material derivative works. So, so this part is Lagrangian and this part is therefore Eulerian. So, this is the Lagrangian fluid parcel, and this is the corresponding Eulerian field representation. This is how to, also visualize the material derivative. Okay. Then the fluid acceleration, we always did it with a scalar, but if it is applied to a vector, for example, that vector is v, or the velocity, then this is the quantity that you get. So that gradient of a velocity is a tensor, but here it can be treated in a simpler way. So if you look at this du by dt, or the first or the x direction, for example, that is u, so you get this particular term, right? Okay, so and then you have the y and the z. So all of these shows this is the family of the family of equations that you see. Okay, so in order to calculate the velocity of a fluid element, what do? If you, for example, if r is xi, yj, and zk, so if you take the material derivative of that, you get this. So in other words, this is the, considering each component in the Cartesian as a scalar, you get this particular form. Okay, so in other words, if you look at it, so there is the convective derivative is actually so the actual, that is the acceleration term, basically what we are talking about. Then of course we have the transport. So in this case, the transport phenomena, the concept of system, and this is the control volume, the dotted line. So the system is a collection of matter of fixed identity, always the same atoms or fluid particles. Control volume is a geometric entity and it is independent of mass. So the conservation laws are like this. So this is the conservation of mass, momentum, angular momentum, and conservation of energy. So the laws applies to either solid or fluid systems, ideal for solid mechanics. But in fluids, you need to bring the control volume approach for a specific, because you want to apply it to a specific region of the fluid of interest. So then we have the Reynolds transport theorem, which basically establishes the link between system and control volume. So for moving or deforming control volume, any rate of change of any property B, which is an extensive property, is given. This is beta is an intensive version of the same property. So it is the rate of change of that particular thing within the control volume and whatever is coming out, the flux that is coming out of the control volume, okay, or going into the control volume. Here this VR is a V relative velocity, and this is a dot product with respect to the area. So this is basically a scalar dot product. So basically you have the flux which is normal, or a component of the flux which is normal to the area. So there are special cases. There can be non-deforming, moving control volume, etc., etc. There can be fixed control volume. There can be steady state control volume. For steady state, of course, this will be equal to 0. Okay, so for a steady state control volume. All right. So if you look at these equations, these are the equations for, if when you have a fixed control volume, this is the equation. So the flux terms is basically nothing but whatever is going out minus whatever is going in. So that is all there is to it. So remember, this is across the control volume. So it's a volume integral. This is a surface integral. Okay, so now mass, when you have the corresponding beta is 1. When you have momentum, it is just the velocity, the beta, that is the intensive variable, and when it is energy, it is E, right? So so that is those are the nomenclatures. So you can use the conservation principles, like from conservation of mass, for a system like this, for a system where there is a couple of inlet and 2 outlets. It's like a pipe. You can think about it like a pipe. So dm by dt is equal to 0. For this case, m equal to 1, so beta is equal to 1. So if you do the Reynolds transport theorem, you will see that this is equal to 0. So for a fixed control volume, this is equal to 0. Okay. So now now if you now do this, there are two inlets, two outlets. So if it just becomes rho AV. So rho into A into velocity minus whatever is going out plus whatever is going in. So for a fixed control volume steady state, this is the equation that you have that is actually going on. Okay, for a fixed control volume. Okay. Similarly, you have a conservation of mass in conservation of momentum. In this case, the intensive variable beta is v, and the extensive variable is mv. Again, you apply the Reynolds transport theorem. You have force, external force is equal to ma. So this is basically the acceleration term. Again, it's the same thing that you see over here. This is v, and remember, this is the relative velocity. So you for a fixed control volume, this is what you get. Okay, this v becomes capital V now. And so here in this case, you sum total all this stuff. Okay, and the force external will be the rate of change of momentum, or the change of momentum. So that is what you get. Whatever is out minus whatever is in, that will give rise to the force over here. And if it is a steady state, so that unsteady terms actually drops out. Okay. So similarly, you can have conservation of energy as well. So it is like, Q added to the system, W is the work done by the system. So this is the first law of thermodynamics, as we all know. So similarly, you can write this expression. I'm not going to go into the details of all of this. You can use the Reynolds transport theorem once again for this. Okay, but this time it is, the rate of change of energy is equal to Q minus dW by dt is equal to all these energy terms. Okay, so so dQ by dt is the heat input. This is the work done. And then you can write this equation. Okay, this you can see in any heat transfer book. So ultimately, at the end of the day, you get something like this. Okay, for a steady state kind of a system, this you already know that the heat transfer minus the work minus the viscous dissipation is this, something like this. If m1 dot is equal to m2, whatever mass is entering is actually exiting, you have something like this. So this is the steady flow version of the SFEE. In general, multiple inlets are there. Then if you have to do the summations. Okay, so then these are the conservation laws in integral forms. This is what you need to know. Okay, so this is the F equal to ma basically. So all of them share that general form which involves beta. So now there is a specialized form which we also discussed, that Bernoulli's equation. So Bernoulli's equation is along the streamline, friction or inviscid flow, and incompressible or constant density. So if it's an unsteady flow, okay, this is called the Euler's equation, and for a steady flow, the integral part of this is called the Bernoulli's equation. The whatever is in the bracket is basically the Euler's equation. Okay, so if your flow along the streamline, you can apply Bernoulli's at two different points, okay, of the flow field. This is routinely used where you have a balance between pressure head, velocity head, and the potential head. Okay, so you can also have the differential forms of these quantities, and you can derive them from the integral version by using the divergence theorem, and then you can shrink them to a point. So this is what you get. So this is the conservation equation, and if it is incompressible, the volumetric dilatation is actually equal to 0. So similarly, you do the same thing with the momentum equation. Okay, and you get ultimately this. This is the stress term. This is the tensor. Okay, and so tau ij is written like this: tau xx yy, these are the normal stresses, where the other ones xy are the shear stresses. So moment you substitute all of them, you get something like this, which is the Navier-Stokes equation. This is the viscous term, this is a substantial derivative, which is the acceleration term, this is the pressure, and this is the body force. So if it is inviscid, you will get the Euler's term, because the viscosity will actually drop off. Then the conservation can be also written in a form like this: H is the enthalpy, phi is the viscous dissipation. It can be neglected in certain cases because you can see it depends on the square of the velocity gradient, but not the cross velocity gradient. So these are the equations in its in the differential forms. The conservation of mass, conservation of linear momentum, and conservation of energy. Okay, so we will end our lecture over here, where we actually have covered a lot in terms of that what these quantities are, and we have already covered, mathematically we have shown that how these can be best illustrated, but this is just a summary, very quick summary, because in measurement you are supposed to measure all these things, and you are supposed to have an idea that what we are trying to measuring, either it's a field measurement or it's a Lagrangian type of a measurement. Mostly ours are field measurements.